Hi students, welcome to the third lecture in permutations and combinations. I hope you have watched the first two lectures. If not, watch the first two lectures and then come back to lecture 3. So in this lecture we are going to do a few more problems on permutations. So before going into this lecture, let me recall what we have done in the first two lectures. So in the first two lectures we have discussed about fundamental principle of counting. Fundamental principle of counting. So both addition and multiplication. So what does this fundamental principle of counting say? If a task T contains two different works, W1 and W2, and the number of ways of doing W1 is M and number of ways of doing W2 is N, then the number of ways of completing the task is equal to number of ways of completing W1 times number of ways of completing W2. Okay, and coming to the addition part, if a task T can be performed in two formats, W1 or W2, then the number of ways of completing the task is equal to number of ways of completing W1 plus number of ways of completing W2. So this is about fundamental principle of counting. And then we have defined factorials. Factorials are defined for non-negative integers, and 0 factorial is defined to be 1, and n factorial is defined as n times n minus 1 factorial. So if you want to define 4 factorial is equal to 4 times 3 factorial, which is equal to 4 times 3 times 2 factorial, which is equal to 4 times 3 times 2 times 1. So you can just leave it as it is. You don't need to remember the value of 4 factorial and 5 factorial and so on. And then we have discussed about linear permutations and circular permutations. Linear and circular permutations. So linear and circular permutation, if you arrange things in a row, then it's going to be a linear permutation. If you arrange things in a circle, it's going to be a circular permutation. And then we have discussed about the differences between linear permutations and circular permutations. And then we have a theorem to count number of linear permutations. So number of permutations of n distinct objects taken R at a time is denoted by NPR, and which is equal to n times n minus 1 times n minus 2 so on up to n minus R plus 1. So if you want to express, we can modify this one and we can express this as n factorial upon n minus R factorial. So this NPR stands for number of permutations of n distinct objects taken R at a time. And by convention we define NP naught to be equal to 1. And we have seen that NPN turns out to be n factorial. And then we have discussed a few theorems on NPR. NPR you can write it as n times n minus 1 p R minus 1. So we have given two different proofs for this one. And the next theorem that we had here is NPR is equal to n minus 1 PR plus R times n minus 1 P R minus 1. So here you have to understand what does this term R times n minus 1 P R minus 1 stands for. R times n minus 1 P R minus 1 stands for number of permutations of n distinct objects taken R at a time which always contain a particular element. I repeat, R times n minus 1 P R minus 1 stands for number of permutations of n distinct objects taken R at a time which always contain a particular element. So here n minus 1 P R stands for number of permutations of n minus 1 distinct objects taken R at a time, or else you can read this one in other way, that is number of permutations of n distinct objects taken are at a time which do not contain a particular element. And here NPR stands for number of permutations of n distinct objects taken are at a time. Therefore, number of permutations of n distinct objects taken are at a time is equal to number of permutations of n distinct objects taken are at a time which do not contain a particular element plus number of permutations of n distinct objects taken are at a time which always contain a particular element. And then we had done few problems on permutations. So in those problems, what we have to do is first we have to give importance to the constraint. First we have to fix the constraint and then we have to proceed to the problem. So these are the things that we have discussed in lecture 1 and lecture 2. I hope you are familiar with these things. Okay, now let us move on to the next thing. Let us look at the first problem. So here the first problem is if NP4 is equal to 1680, then find n. I repeat, if NP4 is equal to 1680, then find n. So in general, NP4 stands for NP4 is equal to n factorial upon n minus 4 factorial, or else you can just write it as n times n minus 1 times n minus 2 times n minus 3. So this is the expansion of NPR or NP4. Now here NP4 is equal to 1680. So this implies n times n minus 1 times n minus 2 times n minus 3 is equal to 1680. So we have to solve this equation. So you have already studied about the quadratic expressions and theory of equations. Now if I expand this LHS, so this LHS is going to be a 4th degree polynomial. This LHS is going to be a 4th degree polynomial, and solving quadratic equations is easy. Solving cubic equation is little bit difficult, and solving biquadratic equations is little bit hard. So it is going to be a biquadratic equation, that is the degree of this polynomial is going to be 4. So it's little bit hard to solve this polynomial equation. So we will not expand this one and we will not solve it using the techniques of theory of equation. We will do trial and error. Okay, so here we have n times n minus 1 times n minus 2 times n minus 3 is equal to 1680. So basically what we have to do is we have to express 1680 as product of 4 distinct numbers, and these 4 distinct numbers should be consecutive numbers. So let us see whether we can able to find such numbers or not. Okay, so this 1680 I can write it as 2 times 840, but here I have only 2 components, so let me express again. So which is equal to 2 times, let me write it as 4 into 210, but here also we have only 3 numbers, so which is equal to 2 times 4 times 210, I can write it as 3 into 70. Okay, so now I can able to write 1680 as product of 4 numbers, but unfortunately these 4 numbers are not consecutive numbers. So splitting 1680 in this way is not going to help us. So let us see whether we can split 1680 in some other way or not. One 1680 is equal to, so 10 into 168. So this one I can write it as 10 times 8 into 21. So we can able to express 1680 as product of 3 numbers. But we have to express 1680 as product of 4 numbers. So let me expand it one more time. So 10 times 8 times we have 21. So 21 I can write it as 7 times 3. Now 1680 I can able to express it as product of 4 distinct numbers. But here also unfortunately these 4 distinct numbers are not going to be consecutive numbers. But we have come little bit close. We have 8 and 7. These two are consecutive numbers and there is one gap. So 10 and 8. We don't have 9. So let us see whether we can able to get any 9 or not. So if not, we have to modify. So this one I can write it as 10. I can write it as 2 times 5 times 8 times 7 times 3. But this is not going to help us because we are expressing 1680 as product of 5 distinct numbers. Our motto is to express 1680 as product of 4 distinct numbers. So we have 8 and 7. So is there any possibility to get 9? We have only 1 3. So there is no possibility of getting 9. So let us see whether we can able to get 6 or not. So we have this 3 and we have this 2. Therefore I can able to get 6. So this one I can express it as 5 times 8 times 7 times 6. So here we have succeeded in writing 1680 as product of 4 distinct numbers. But here the numbers are not in order. Let me write the numbers in order, which is equal to 8 times 7 times 6 times 5. So this implies n times n minus 1 times n minus 2 times n minus 3 is equal to 8 times 7 times 6 times 5, or else you can write it as 8 into 8 minus 1 times 8 minus 2 times 8 minus 3. So this implies our n is equal to 8. So we have few problems based on this one. So all that you have to do is you should expand NPR. Okay. So let us move on to the next question. Okay. If 12PR is equal to 1320, then find R. Okay. So what does this 12PR stands for? 12PR is equal to, I can write it as 12 factorial upon 12 minus R factorial, or else I can write it as 12 times 12 minus 1 times 12 minus 2 and so on up to 12 minus R plus 1. So this is the expansion of 12PR. Now what is the information that we have? 12PR is equal to 1320. So here what we have to do is we have to express 1320 as product of consecutive numbers starting from 12. So let us see whether we can able to express it or not. So 1320 I can write it as 12 times 110. So after 12 I should get 11. So let us see whether 11 we can get a factor of 11 from 110 or not. So which is equal to 12 times 11 times 10. Now 1320 I can able to express it as product of 3 consecutive numbers starting from 12. This implies 12PR is equal to 12 times 11 times 10. So 12PR is equal to 12 times 11 times 10. So we have expressed is as product of three consecutive numbers. So this implies R is equal to 3. R is equal to 3. So these are few problems based on the formula of NPR. So let us go to the next problem. Okay, so the next problem is like this. If the ratio of n plus 1 p5 is to np5 is equal to 3 is to 2, then find n. So in the earlier problems we have only one term, but here we have two terms, and they have given the ratio of these two terms. The ratio of these two terms is equal to 3 is to 2. Now we have to find n. So let us expand this one. N plus 1 p5 is equal to n plus 1 factorial upon n plus 1 minus 5 factorial, which we can write it as n plus 1 factorial upon n plus 1 minus 5, which is nothing but n minus 4 factorial. Next we have np5. np5 I can write it as n factorial upon n minus 5 factorial. Now in the question we have the ratio of these two. The ratio of these two, n plus 1 p5 is to np5 is equal to 3 is to 2. So which we can write it as n plus 1 factorial upon n minus 4 factorial divided by n factorial upon n minus 5 factorial is equal to 3 is to 2. Now let us rewrite these terms. So what we have is n minus 1 factorial upon n minus 4 factorial into n minus 5 factorial upon n factorial is equal to 3 upon 2. Now n plus 1 factorial I can rewrite as n plus 1 times n factorial. And coming to these two, n minus 4 factorial and n minus 5 factorial. So which one is big? And is n minus 4 factorial big or n minus 5 factorial is big? So in order to compare these two, we have to compare only n minus 4 and n minus 5. So n minus 4 is bigger than n minus 5. So we have to expand n minus 4 factorial. So n minus 4 factorial I can write it as n minus 4 times n minus 4 minus 1 factorial, which is nothing but n minus 4 times n minus 5 factorial. So we can rewrite these, we can use these terms here. Now this implies n plus 1 factorial I can write it as n plus 1 times n factorial upon n minus 4 factorial I can write it as n minus 4 times n minus 5 factorial into n minus 5 factorial upon n factorial is equal to 3 upon 2. So these n factorials get cancelled and n minus 5 factorial get cancelled. So what is left out here? N plus 1 upon n minus 4 is equal to 3 upon 2. Now we can cross multiply and we can solve. 2n plus 2 is equal to 3n minus 12. So this implies 2 plus 12 is equal to n. or n is equal to 14. So this is your answer. So the only thing that you have to take into consideration here is how to expand n minus 4 factorial and n minus 5 factorials. Anyway, we are not expanding n minus 5 factorial, we are expanding n minus 4 factorial. So n minus 4 factorial, I can write it as n minus 4 times n minus 4 minus 1 factorial, which is nothing but n minus 5 factorial. And n plus 1 factorial, we can write it as n plus 1 times n factorial. Next also we have a similar kind of question. 56p r plus 6 is to 54p r plus 3 is equal to 30800 is to 1. Then find r. In the previous problem they are asking us to find n. Here they are asking us to find r. So let us see how we can do this one. So 56p r plus 6, I can write it as 56 factorial upon 56 minus of r plus 6 factorial is to 54 factorial upon 54 minus of r plus 3 factorial is equal to 30800 is to 1. So which implies 56 factorial upon 56 minus of r plus 6 is nothing but 50 minus r. 50 minus r factorial. So we can rewrite this term as 54 factorial. So here division is becoming multiplication, so I am inverting the fraction. So 54 factorial, and here we have 54 minus of r plus 3, which is nothing but 51 minus r factorial is equal to 30800 by 1. So here we have 56 factorial and here we have 54 factorial. So this 56 factorial I can write it as 56 times 55 times 54 factorial. And coming to these two terms, 50 minus r factorial and 51 minus r factorial. So what we have learned is we have to expand the bigger one. So out of 50 minus r factorial and 51 minus r factorial, 51 minus r factorial is bigger. So 51 minus r factorial, I can write it as 51 minus r times 51 minus r minus 1 factorial. So which is nothing but 51 minus r times 50 minus r factorial. So let us use these two expansions and rewrite again. So here we have 56 factorial, I can write it as 56 times 55 times 54 factorial upon 50 minus r factorial. So here 51 minus r factorial, I can write it as 51 minus r times 50 minus r factorial upon 54 factorial is equal to 30800 upon 1. So these 54 factorials gets cancelled and 50 minus r factorial gets cancelled. So what is left out here? 56 times 55 times 51 minus r is equal to 30800, or 51 minus r is equal to 30800 upon 56 times 55. So this 55 I can write it as 5 times 11, so which is equal to 56 times 5, and then here we have 2, 8, 00. So this 56 is nothing but 28 twos. So which is, I can write it as 100 upon 2 into 5. So which is nothing but 10. So 51 minus R is equal to 10. This implies R is equal to 51 minus 10, which is equal to 41. So in the previous problem they are asking us to find out N, and here they are asking us to find out R. Till now we have seen few problems related to the expansions of NP-R. Now we are going to look into few interesting problems related to permutations. Now before going into real problems, so let us look into few things so that these things will be helpful in understanding the next problems. Okay, now let us answer this question. In how many ways I can arrange the letters A, B, C, D? So we have already seen this question. A stands for Abhi, B stands for Bobby, C stands for Chanti, and D stands for Dhruv. These four wants to play gully cricket. So in how many ways we can arrange these A, B, C, D? That is the question. So we have already seen the answer. The answer is going to be 24. Anyway, we'll look into that answer again. So I have these objects A, B, C, D. So I have 4 objects, and I have to arrange these 4 objects. I can arrange these 4 objects in 4 blanks. I have 4 objects and I have 4 blanks. Therefore N is equal to 4 and R is equal to 4. Therefore the answer is going to be number of arrangements is equal to NPR, which is equal to 4P4, which is equal to 4 factorial, and which is same as 4 times 3 times 2 times 1, which is nothing but 24. And in the first class we have elaborated, or we have listed down all these 24 permutations. Now let us look into the second question. In how many ways we can arrange the letters A, B, C so that A and B always come together? So if I don't impose this condition, A and B always come together, then what is the answer that we are going to have? The number of ways of arranging the letters A comma B comma C is, or number of ways of arranging the letters of the letters A, B, C is 3P3, which is equal to 3 factorial, which is equal to 3 times 2 times 1, which is equal to 6. So in the previous question we have 4 distinct objects, and we have to arrange these 4 objects. Sorry, we have to arrange these 4 objects. So the number of ways of arranging is 4P4, which is equal to 4 factorial, and which is 24. Now here the number of ways of arranging A, B, C is equal to 3P3, which is equal to 3 factorial. But notice that I haven't imposed the condition that A and B are together. Okay, first let us write down these 6 different arrangements. The 6 different arrangements that we are going to have are A, B, C, A, C, B. And the next one is B, A, C, B, C, A. And the next one is CAB and CBA. So these are the 6 different arrangements that we are going to have. Now let us look into that condition. So what is the condition that we have? The condition is A and B should come together. We have these 3 distinct letters A, B, C, and the condition is A and B should come together. So whenever you have constraints like this coming together, what you have to do is we have to group these two things. Now how many groups we have? The first group contains A and B, and the next one is C. So on the whole we have only 2 distinct objects. 2 objects. So if you are getting confused with 2 objects, I can say that 2 units. The first unit contains A and B, and the second unit contains only C. Now in how many ways I can arrange these 2 units? Number of ways of arranging these 4 letters is equal to 4p4, which is equal to 4 factorial. Number of ways of arranging these 3 letters A, B, C is equal to 3p3, which is equal to 3 factorial. Now number of ways of arranging these 2 units. Number of ways of arranging is equal to arranging is equal to 2p2, or else we can just write it as 2 factorial, which is nothing but 2 times 1. So let us see what are those 2 arrangements. So the first arrangement is, I am writing the first unit first. First unit means I can write AB first and then C. And the second arrangement is C is coming first and then we are having AB. But unfortunately these are not the only options that we have. We have 2 more options. The 2 more options that we have is, in this one I can still write BAC. So here ABC we have, and here we have BAC. In both the arrangements A and B are together. So here also we have CAB. So, and one more arrangement we are going to have is CBA. Okay. So in both these arrangements A and B are together. So on the whole, if I ask you in how many arrangements A and B are together, the answer is going to be 4. But here we have only 2 arrangements. So the mistake that we are doing here is we are not arranging A and B in this unit. We are treating A and B as a single unit. But in this single unit, I can rearrange A and B in 2 ways. I can rearrange A and B in 2 ways. Therefore, the total number of arrangements in which A and B come together is equal to 4. It's not 2, it is equal to 4. Why the answer is 4 is 2p2. The complete answer is 2p2 times 2 factorial. Why we have this 2 factorial means I can arrange A and B in this unit. I can arrange A and B in this unit in 2 ways, or 2 factorial ways. Therefore, the total number of arrangements is equal to 2p2 into 2 factorial. Okay. So let me ask one more question and check whether you have understood or not. In how many ways I can arrange the letters of the letters A, B, C, D? So here the answer is going to be 4 factorial, which is equal to 24. Now if I impose the condition that A, B, C are together, A, B, C come together. A, B, C come together means what you have to do? We have to tie up A, B, C. We have to treat A, B, C as a single unit. If you treat A, B, C as a single unit, so I am writing the answer here. If I treat A, B, C as a single unit, now the total number of units that we have is 2. I can arrange these 2 units in 2 different ways, or I can arrange these 2 units in 2p2 ways. And I can arrange ABC among ABC in 3 factorial ways. I can arrange ABC among ABC in 3 factorial ways. Therefore, the total number of ways is equal to 2p2 into 3 factorial, which is equal to 2 times 6, which is equal to 12. So I encourage students to write down all these 12 different arrangements. So I hope these two questions are clear for you. The first question is, in how many ways we can arrange the letters A, B, C, D? So the number of ways of arranging the letters A, B, C, D is equal to 4p4, which is equal to 4 factorial, and 4 factorial is 24. So why we have this 4p4 is we have 4 objects A, B, C, D, and we have to arrange these 4 objects in 4 blanks. And I can arrange these in 4p4 ways, which is 24. Now coming to this question, second question. So in how many ways we can arrange the letters A, B, C so that A and B come together? So here we have to arrange A, B, C. If there are no constraints, then the answer is going to be 3p3, which is 3 factorial. But here we have the constraint. The constraint is A and B should come together. Whenever you have constraints like this, what you have to do is you have to group A and B together, or you have to group all those objects which are supposed to come together. So here A and B are supposed to come together, so you have to group A and B. Once you group A and B, we have still 3 different objects, but we are treating these 3 different objects as 2 units. So we have these 2 units, and we can arrange these 2 units in 2 factorial ways, or 2p2 ways. So these are the 2 ways that we can arrange. But unfortunately, in this 1 unit, we can rearrange A and B in 2 ways. The first arrangement is AB and the second arrangement is BA. So here also in this arrangement, I can write CAB and I can have CBA. Therefore, the total number of arrangements in which A and B coming together is equal to 4. It is not 2 factorial. It is not 2 factorial. The mistake that we are doing here is we are not rearranging the terms inside that unit. If you rearrange the terms inside that unit, then that complete answer is 2p2 into 2 factorial, which is equal to 2 times 2, which is equal to 4. And these are the 4 arrangements that we have. Suppose we have these 4 objects A, B, C, D, and the requirement here is A, B, C should come together. Then what we have to do? We have to group this A, B, C together. So once you group this A, B, C together, you can group this A, B, C together. Sorry. Okay. So once you group this A, B, C together, we can have only 2 units. The 2 units are A, B, C is 1 unit and D is the other unit. I can arrange these 2 units in 2 factorial ways. But among this unit, A, B, C, I can arrange this A, B, C in 6 different ways, or 3 factorial ways. Therefore, the total number of arrangements in which A, B, C should come together is equal to 2p2 into 3 factorial, which is equal to 2 times 6, which is equal to 12. So I encourage students to write down these 12 arrangements so that you will get some clarity. Or else I have listed down these 12 arrangements in the notes. You can have a look at it. Okay, let us move on to the next question. The next question is, in how many ways we can arrange 9 mathematics papers so that the best and the worst paper should always come together, may not come together. So let me explain the question for you. There are 9 students in the class. 9 students in the class. And I have conducted mathematics exam for these 9 students. And therefore I can have 9 papers. And now I have evaluated these 9 papers. After evaluating these 9 papers, I have announced the best paper. The best paper, let me label the best paper as A, and the worst paper. and the worst paper as B. The best paper I am labeling it as A, and the worst paper I am labeling it as B. Okay. Now I have to distribute these papers in the class. I haven't arranged the papers in order, so I have a zigzag manner, and I have to distribute these papers. Now the question is, in how many ways I can distribute? So in this there are two constraints. The first one is the number of ways of distributing such that, or in how many of them the best and the worst paper will come together. The next question is may not come together. First let us ignore the constraint and answer the question. Number of ways of arranging nine papers is equal to 9p9, which is equal to 9 factorial, if there are no constraints. Now let us answer the first question. The first question is the best paper and the worst paper should come together. So if the best paper and worst paper come together, what I can do is I can ask the best performer to explain few things to the worst performer, or I can ask the worst performer to seek help from the best performer. So this is the thing. Okay. Now the best paper and the worst paper should come together. So whenever you see the constraint like coming together, what you have to do is you have to tie these two things. If you tie these two things, then how many units of papers we have? The first thing that you have to do is tie up the best and the worst paper. Now how many distinct papers we have? We have still 9 distinct papers, but we can treat these 9 distinct papers as 8 units of papers. Why we have 8 units of papers? Because out of those 9 papers I am removing these 2 and treating those 2 as 1. On the whole we have 9 distinct papers, but out of those 9 distinct papers I am removing the best paper and the worst paper. Removing in the sense I am tying up these 2 papers together. Once I tie these 2 papers together, what I have is I have still 9 distinct papers, but out of these 9 distinct papers I can just treat it as 8 units of papers. So in the previous question also, here we have A, B, C. These are 3 distinct objects. But what I am doing is I am tying up A and B. Once I tie up A and B, I have only 2 units of papers, or 2 units. The first unit consists of AB and the second unit consists of C. So here also we have 9 distinct papers. Out of these 9 distinct papers, what I am doing is I am tying up the best paper and the worst paper. So if I tie up the best paper and the worst paper, I can still have 9 papers, but I can treat these 9 papers as 8 units of papers. Now in how many ways I can arrange these 8 units is the question. Number of ways of arranging these 8 units is equal to 8p8, which is equal to 8 factorial. But I don't want to arrange these 8 units together. I want to arrange all the 9 papers together so that the best and the worst paper come together. Now within that one unit consisting of the best paper and the worst paper, I can rearrange these two in 2 factorial ways. I can rearrange these two in 2 factorial ways. Therefore, in the one unit containing the best and the worst paper, I can rearrange them in 2 factorial ways. So this implies number of ways of arranging the papers. Is equal to 8 factorial times 2 factorial. Or else you can treat it as this one, like this. W1 is to treat this, is to arrange these 8 units of papers, and W2 is to arrange those 2 papers in that unit among themselves. So therefore the total number of arrangements is equal to 8 factorial times 2 factorial. Now coming to the second question. So what is the second question that we have? The best and the worst paper should not come together. So while distributing the papers or while arranging the papers, I don't want to mix these 2 papers. I don't want these 2 papers to come simultaneously. So I don't want to see the worst paper immediately after the best paper. And similarly, I don't want to see the best paper immediately after the worst paper. The total number of arrangements is going to be 9 factorial if there are no constraints. If we impose the first constraint, in the sense the best paper and the worst paper coming together, the total number of arrangements is equal to 9 factorial, and the number of arrangements in which these two come together is equal to 8 factorial times 2 factorial. Therefore, the number of arrangements in which these two do not come together number of arrangements in which the best and worst do not come together is equal to total minus number of ways in which they come together. So this implies the answer is 9 factorial minus 8 factorial times 2 factorial. 9 factorial minus 8 factorial times 2 factorial. So you have to understand this problem thoroughly. So let me state the problem again. In how many ways we can arrange 9 mathematics papers so that the best and the worst paper will always come together, the best and the worst paper will not come together. Now if we don't have these constraints, the number of ways of arranging these 9 papers is equal to 9p9, which is equal to 9 factorial if we don't have any constraint. Now let us move into the first constraint. The first constraint is the best and the worst paper should come together. So whenever we have the constraint like coming together, what we have to do is we can tie up these things. Now once you tie up these 2 papers, on the whole we have 9 papers, still we will have 9 papers, but I can treat these 9 papers as 8 units of papers. The 8 units of papers are these 2, I can treat it as 1 paper, and the remaining 7 I can treat it as individual units. Therefore the total number of units of papers we have is 8, and I can arrange these 8 papers in, or 8 units in 8 factorial ways. And in this unit I can rearrange A and B. I can rearrange A and B in 2 factorial ways. A and B means I can rearrange the best paper and worst paper in 2 factorial ways. I can keep the best paper on the top and the worst paper on the bottom, in the bottom. Or else I can keep the worst paper on the top and best paper in the to the bottom. So the total number of arrangements in which the best paper and the worst paper will come together is equal to 8 factorial times 2 factorial. Now coming to the second part, the total number of arrangements in which the best and the worst paper will not come together is same as the total number of arrangements minus the number of arrangements in which those two come together, which is equal to 9 factorial minus 8 factorial times 2 factorial.